So my name's Pat. Today we're going to be talking more about the periodic table and other things in the periodic table to include electron configuration, electronic geometry, molecular geometry, VSPER theory, and quantum numbers. If we have time at the end, we're going to talk about general trends in the periodic table. So let's start with just a quick review of what we spoke of in the other class. I'm going to draw a rough sketch of the periodic table now. So remember, we have our periodic table here. This is my best attempt at drawing the periodic table here. We have our series of metals over here. We then have a stair-step line starting from here that comes down. This is going to separate our metals from our non-metals. These would be your non-metals over here. These will be your metals over here, with the exception of hydrogen. It might be handy on the back of your hand. That's always something that they can't make you take off in the testing center. But yeah, periodic tables, not a bad thing to know. So we have metals on this side, we have non-metals. Now remember, along this stair-step line, we have a group that are known as metalloids. That includes things like aluminum and silicon that have some metallic properties and some metallic properties. Thank goodness silicon, well, because silicon has some metallic properties, but it doesn't heat up like a lot of metals, that's why a lot of microchips are made out of silicon. You can run an electric current through them. We talked about some of our common families. You have your alkali metals in this column, then you have alkali earth. We have what's in here are called our transition metals. And over here, we have halogens in one column here. And right here, starting with helium up top, we have our noble gases. Remember, these are going to be positive. The first column is +1. The next column is +2. Over here, we start usually your noble gases are 0. Then you would have a -1, -2, -3, and so forth. We have different numbers, positives on this side, negatives on this side. What we're going to talk about now is electron configuration. Now, electron configuration is generally broken down into 4 subshells. Our 4 subshells are S, P, D, and F. Remember, there are 2 columns down here. These are generally our rare earth elements and a lot of the radioactive series, the lanthanide and the actinide series. Now, these subshells refer to different areas of the electron. So over here on this area of the periodic table, the first 2 columns will be S. And S can hold 2 electrons. The next column that comes in, the P, will be this block here. I'm going to try and draw our block here, starting with boron and aluminum in that column, all the way over to our noble gases. So this column here, or that block there, that will be our P block. P can hold 6 electrons. The next column, right through here, what are our transition metals, what we labeled transition metals? Those are our D block. That will be our D subshell. Now our D subshell can hold 10, and if you count from scandium at number 21 over to zinc at number 30, that's why D has 10 across there. That can hold 10 electrons. Our last block, our F block, is this block that is set out aside, our lanthanide, our actinide series. This is where you find things like uranium and plutonium and your rare earth elements that you've probably never seen, like neodymium, can be used to make magnets, or promethium, coming from Prometheus. They're getting pretty desperate by the time they're pulling Prometheus into the periodic table. So the F block can hold 14. I'm just going to write out 14 electrons. So if you were to write an electron configuration, say for hydrogen, we would write hydrogen here. You could say H, and then you could have an S. You could have a series of P. You could even have 5 Ds. And you could get into 7 Fs. Because another key critical element of this is each orbital, move this up, each orbital can hold 2 electrons. Each orbital has 2 electrons total. So you have 2 columns here because in this column right here you have 2 because you have 1 s orbital, you have 3 p orbitals, 5 d orbitals, and 7 f orbitals. If you think about this, your number of orbitals is just a series of your first series of odd numbers. So our orbitals for each one, s is 1, p is 3, d is 5, and f is 7. So because our H is right here at the top, all we have for H for an electron configuration would be 1 arrow going up. If we then want, so you wouldn't even write these, I just wrote these for just general clarification of what it's going to look like. When we get to helium, helium has 2, so helium would be 1 going up and 1 going down, and now your orbital is full. Now, if we wanted to do lithium, you'd have to draw out lithium. You'd have your 1s, because this is your first column across. Your top column across will be, that will be energy level 1. Your second column starting with your lithium will be 2. Your next column starting with sodium will be 3. Your next column starting with potassium would be 4. So if we were to do lithium, we would say, well, it already filled our first 2, so we would have 1 arrow going up, and then 1 arrow going down. And then we would have to start 2s, so I'd say 2s, just 1 up. Let me show you a very common one that we wind up using a lot. I'm going to show you carbon. Carbon, our first energy level fills, our H and our S fills, so that gets a 1s. It has 2 electrons in there. But now we get to carbon, which is in our second row across. So we have our 2s, which would be 1 up and 1 down. And then we move over into, if you look where carbon is over here in this P block section of the periodic table. So over here in this P block section, we find our carbon. So we'd write 1, 2, 3. This would be labeled 2p. And carbon would be 1, 2. We're not going to pair up our electrons until we have to. And in fact, while this is carbon's normal state of 2s, 2 electrons in the 2s, and 2 electrons in the 2p, it will hybridize out, which means you would actually have carbon in your outer valence shell, which is your outermost shell, which would be our p shell right here. That would be our outermost shell. We would now show carbon as 1, 2, 3, 4, because you have 4 electrons in the outermost shell, which is when we talked about our Lewis structure. That's why when you write carbon, you have 1, 2, 3, 4 solo electrons on carbon. Those 4 solo electrons on carbon mean that you will get 4 bonds on carbon if carbon gets to do what it wants to do. Let's do a nitrogen just to be sure. And then we will do a transition number. We will do a transition metal. I'll pick iron. Iron's a good one to do. But if we had nitrogen and we were asked for our electron configuration, we would say, well, nitrogen obviously has its first level completely filled, which is just the 1s. Then we come down and we find nitrogen is in the second level. So we say it has a 2s and it has a 2p, 1, 2, 3. It fills both of its s's when it passes through lithium and beryllium. So that's an electron up, an electron down. And then if you look at where nitrogen is, it comes over 1, 2, 3. This is why nitrogen, written as a Lewis structure, will be written as 1, 2, 3, 4, 5. 5 total electrons in its electron configuration. Only one set is paired, which gives us a place for 3 bonds, which is why you see things like NH3, ammonium. I'm now going to do iron. So let's look at iron's electron configuration. So I write my formula for iron. Now we find iron on the periodic table. If you have a periodic table, it's great to follow along. If you don't have a periodic table, it's helpful. Maybe you can find one on the cover of your book, or if you can just envision what I'm doing, I'm saying, here's my H, lithium, so this is 1, this will be 2, this will be 3, and now we get on down into iron, which is going to be at least the 4 level. So we write our formula, our symbol of Fe, then we say 1s, which that definitely fills. We say 2s. Now we have 1, 2, and our 2s, and then our 2p is completely full because we completely pass through all these boron, carbon, nitrogen, oxygen, fluorine, neon. So real quick, you can go ahead and say 1, 2, 3, 4, 5, 6. That gets your 2s. We're still not to iron. Now we're in the sodium. Sodium and magnesium is our 3s, so that's 1, 2. Aluminum through argon will be our 3p. 1, 2, 3, 4. Oops, 1, 2, 3, 4, 5, 6. I'm getting ahead of myself. And then we come down to our potassium, and our calcium. That is going to be 4s. 1, 2. It has both of them. Now this block in the center, from scandium and all the way down its line over to zinc, this is our D block. And what we're saying is most of the times our S and our P, think of S and P as the students who are doing a good job, they are being promoted, so they are always the same number. Think of D as a bad grade. D is held back 1. So we are in the 4s when we get to here, but our D is going to be held back 1. So this is 4s, but now we have to go back here and we have to write our D, 1, 2, 3, 4, 5. There are 10 in here. There are 2 electrons per orbital. So we have 5 total orbitals. So we're going to count for our D block. We're going to count 1, 2, 3, 4, 5, 6. So we are going to fill this orbital here as 1, 2, 3, 4, 5, because everyone sits in their own seat. They don't pair up and sit next to someone until they have to. And this is 6 there. Because our 4s in our periodic table fills before our 3s, basically because after you get to the 4th energy level, the s's fill before the d's. This is why we could make very solid guesses about what our oxidation numbers were, that this is +1, +2, +3, and over here is -1, -2, -3. We cannot make those guesses about this in here because it may kick off 1 electron, it may kick off 2 electrons, and may kick off 3 electrons. This has to do with the element wanting to be, or the element or the atom wanting to be stable and have some kind of symmetry around it. So it is very hard to guess what your oxidation numbers are once you get into this transition metal series. Best safest case is to bet on knowing your S, knowing your P, and then your D's fill in. And if your D's were confusing, your F's, which are down here, if you have a periodic table, you can actually look that our lanthanide series goes from 57 to 72. This is basically inserted right here. This first column that runs from 58 to 71 is inserted right here. The second row here is inserted between 89 and 104. So the D's and the F's, there is not a consistent pattern into what their charges are and what their oxidation numbers are. But you won't likely be given that. That would not be something that I would expect to see. They might expect you to see that you would sometimes want to have balance and you're trying to figure out the balance, but that is something that some professors cover it, some professors don't. So now that we understand, or now that we've talked about S, P, and D, F will be the same, let's talk about quantum numbers. And a lot of students hear the word quantum numbers and they get panicked because they've heard about quantum and that quantum mechanics is difficult, and it is. Einstein famously, not that he didn't necessarily disagreed with it, but he famously said about quantum mechanics and what goes along with that, that he refuses to believe that God plays dice with the universe. But we're not looking about something nearly as difficult as God playing a game of dice with the universe. Quantum numbers for our terms, let's think about quantum numbers as a way that you can sit in your lab in New Zealand and look at the behavior of a particular electron around an atom. And I can sit in my lab in Austin, Texas, and look at the particular behavior of an electron around an atom. And if it's behaving the same way, there might be something new that's going on that we don't understand. Or if it's not behaving the same way, you should probably check your instruments, and we calibrate our instruments. What our quantum numbers are a way of identifying the electron. They are a way of identifying an electron. It's almost like a tag and release. That's not the best way of looking at it, but it's basically tag and release kind of system so that we can think of our electrons knowing exactly where they are. And our quantum numbers come down to a series. We have an N, we have an L, we have an M sub L, and then we have an M sub S. Now our N is related to our energy level. When we're looking at our energy level, our N is going to be, this is N equals 1. N equals 1 is just hydrogen and helium. N equals 2. There we go. N equals 2 would be from lithium to neon. N equals 3 would be sodium to argon, and N equals 4 is going to start with potassium. So each time you go down one level on the periodic table, N1, N2, N3, N4. So N is our energy level. Orders of you can think of it as an order of magnitude, but orders of magnitude are more dealing with the powers of 10, base powers of 10. This is an energy level. You can get, if we remember Bohr's atom, I'm going to draw a Bohr's atom out here. This is my nucleus. I have an energy level here. I have another energy level here. I have another energy level here. If you have an electron here, you can put energy into it and move the electron into a new position out here. And as you take the energy out, the electron will fall back down, and when it falls back down, it emits a photon of light. And since light has energy, since light is a combination of frequency and wavelength, the levels are clearly defined. These levels are clearly defined not only by where they are, the row, or rather, the row that they are in the periodic table, but also here it can be defined based upon how far out the electron is from where it normally is. If you excite it beyond its normal energy, like if its energy level is N equals 1, and you put enough energy into it that you excite it out to N is 3, you have very clear, very distinctive places where the electron can be. Without getting too much into quantum mechanics, the jagged little pill of this that Niels Bohr said is that the electron is either here or here. The electron is either here or here. There is no moment where you will not capture a picture, even with the best camera, where the electron is moving from here down to here. The electron's either here or here. So somehow, without traveling that distance that we can visibly see, the electron is here, and then in a blink of an eye, it's here. You're not going to catch an image of it being in between. It has to be at very distinct positions. But that's actually about 3 to 4 weeks away. But that is what quantum is saying, is that the electron is here, then it can be here. Now, for L, the L level, its maximum value, the max value for L is always N minus 1. That is our maximum value for L. It can be less than that, but your maximum value is always N minus 1, which will lead us into some very interesting things that we can make based upon where you are in the periodic table. You can extrapolate based on your L value, whether you're in the S block, the P block, the D block, or the F block. I'll show you that in just a second. Now, our M sub L value will be negative L to 0 to positive L. So whatever your L is, your M sub L has to be between the L value, the negative of the L and the positive of the L, or 0. It can't, if you have an L of 1, you cannot have an M sub L of 2. And the way they ask a lot of questions on the multiple choice test about quantum numbers is they ask a question like, which of the following is not a possible set of quantum numbers? So look for that your M sub L should always be a value between negative L to positive L. Our M sub S, that's our spin. S for spin. And that is either a spin up, which you can say is positive, and that's spin up, or a negative, which is a spin down. And that we can think about is, remember, we have an S, or we have these where they're filled. This arrow is spin up, this arrow is spin down. the L value is going to be related to the subshells. These S, P, D, and F is most commonly what it's going to be associated with. S, P, D, and F. So our L is what's called our angular momentum. We can write that out. So this is energy. And we can think of L as our angular momentum. But for our purposes, we're going to associate with our S, P, D, and F. It says watch what happens. So if I have, say, if my N equals 1, the only possible value I can have for my L when my N equals 1 is 0. And therefore, my only possible M sub L value is 0. And that means that when L is 0, you are always in the S. No exceptions. A lot of times in chemistry, you'll hear about there may be a lot of exceptions. There are no exceptions when the L is 0, you are in the S block. And you only have one orbital. So only one orbital. And then you can have M sub L or M sub S, which can give you 1, 2, which is why your S orbital only holds 2 electrons. If we get to N equals 2, we can have multiple L values. We can have an L of 0, which is fine, or we can have an L, I'm looking at max value, L equals 1. Now, when our L equals 1, we can have an M sub L that is -1, 0, and 1. And each of these can have 2, so that's 1, 2, 3, spin up, 4, 5, 6, spin down. And that's why when your L is 1, you are in the P. If they ask you a question like, what is the maximum value for a P, an electron, a phosphorus electron, we could come back and we could say, well, here's phosphorus. We have our N is 1, 2, 3, so we know our N value is 1. But because it's phosphorus, our L would wind up being, this would be N3, and then L would be 1. And then we would look at it as our maximum value would be, I'm going to write phosphorus here, and then I will do our N for phosphorus is 3. Because it's phosphorus and we're in this P block, our L equals 1. Because it's in P, it must be 1. And then our M sub L, we have a choice of -1, 0, and 1. So we're going to pick our maximum value of 1. And then your M sub S, our first S that fills, is our positive and our spin up. When you have this M sub S, there is not really anything more than just a plus or a minus. This is usually associated with being clockwise or counterclockwise. Let me show you what happens with the D. If we have something, let's say we have N equals, I'm going to say N equals 3. Now our maximum L value for that could be, we could have 2, 1, or 0. So let's say that we have 2, which means that our M sub L values would be -2, -1, 0, 1, and 2. Which gives us 5 orbitals, 2 per each, 2 electrons per orbital, which is why this block across here has 10 in it. 10 spaces, because you can fit 10 electrons. And lastly, the last thing, if we have n equals 4, that means our L can be 3, and then we would have an M sub L of 1, -3, -2, -1, 0, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7 orbitals, which is why if you count these boxes across the bottom, there are 14 from 58 to 71. So key points about quantum numbers. N is energy level. L, max value, is n minus 1. It can be less, but it can never be more. And we can say that if your L is 0, you are in the S. If your L is 1, you are in the P. If your L is 2, you are in the D. And if your L is 3, you are in the F. People ask if there's things greater than S, P, D, and F. There are theories that there are, but we have yet to find them. So as far as we know, they're not. There's nothing greater than S, P, D, or F based on our understanding of this periodic table. Now, let's talk about valence shell. We're going to talk about VSPER theory and electronic and molecular geometries. So VSPER theory, the VSPER theory stands for valence shell pair electron repulsion, which means when we were to if we were to space things out, let's imagine we have something here, and we have two people who can't get along. The maximum space you can put between them would be somebody sitting here and somebody sitting here. Let's not even call them people. Let's just call them areas of electron density. Now, areas of electron density can be they can be one of three things. You can have a pair of electrons. This would be like if we had nitrogen, we had two electrons hanging out there. That's our pair of electrons. They can be a single bond. And a single bond is generally just shown as a line. It can be a double bond. Double bonds are stronger. They have more energy attached to them, and they pull in the atoms closer to each other. The last one that you can have is a triple bond. Triple bonds provide you the greatest energy of all. They are tight. They are very, very tightly bound. And if you've heard of acetylene, that is carbon that is triple bounded to another carbon. It has a hydrogen here. It has a hydrogen here. When you break this bond, these bonds here, you get a tremendous release of energy. You can also think of that as heat. But valence shell pair electron repulsion means that if we were to just have two different areas of electron density, so this is a series of electrons. This is actually CO2. We have carbon with one oxygen here and another oxygen here. They are the maximum distance away they can be from each other. 1, 2, maximum distance away. They completely space out. Acetylene as in that's right. That YNE tells you that it's a triple bonded carbon. Very good. Yes, that's correct, Todd. Maximum distance apart. And we would draw it, if we were to draw a CO2, we would draw CO2 to look like this. Here's our carbon here, double bonded to an oxygen, double bonded to an oxygen. Two areas of electron density. So we would say that this would be SP. when you start talking about hybridizations. There's two areas of electron density. Now, if we had three areas of electron density, I'm going to show three areas of electron density. This is CO2. Let's come down, let's look at three areas of electron density. Let's say we had BH3. BH3 would look like this. Maximum distance apart here is you have 360 degrees, you're in a plane. And so if we were to draw this in an electron in a Lewis dot structure, we'd have boron, we have hydrogen here, hydrogen here, hydrogen here. You're giving everybody, whether there's two, you're giving them a maximum space of 180 degrees. But when there's three, you're giving a maximum space of 120 degrees. And drawing it is not, they don't look a whole lot different on the paper how you draw them when you have two or three. What starts to become different, and because this is three, we would say this would be SP2. So one S and two Ps, three areas. Now the ones that start to depart from what we draw on the paper versus how it looks are going to start with this series. So I'm going to say that we have CH4. So we have carbon, we have a hydrogen here, a hydrogen here, a hydrogen here, and another hydrogen here. That's how we draw it on paper. But I gave it different colors here so that you can see it. If you notice, it spaces out. It's no longer just in a plane. To get the maximum distance away from each other, it goes into 3 dimensions. So if you look at it, it looks like a little sort of, there's always 3 legs on the ground with something coming up, like that. So this would be an SP. There's 4 areas of electron density, so that becomes SP3. And it makes, even though you draw it like this, you are drawing something that exists in 3 dimensions on your paper. This is the reality of what it would look like. Some professors, this may not be if you're in intro chemistry, but in general chemistry, they may want you to start showing it like this, where you have carbon. Let's say we have 1 hydrogen coming up that's in the same plane as carbon. We have 1 hydrogen coming down over here that's in the same plane as carbon. And then you have a darkened line here that is almost showing a hydrogen coming right out of the paper at you. That white one coming right out of the paper. Now the orange one that is going back and away from you would be drawn by this little hatched line. And that is an attempt to show that you're giving, this is existing in 3 dimensions. It's no longer in a plane like the SP2 or the SP. They're no longer in a linear flat plane. It's now coming out of the plane like so. We also have, I see where it says, we also have SP3D, which would be 1, 2, 3, 4, 5. This would be an SP3D. I'm going to set this down right here. If you notice, it has, well, actually, I'm going to show you this. It has 1, 2, 3, and then we have an electron going up and an electron going down. So we have 1, 2, 3, 4, 5 areas of electron density. You typically see this with a d-octet expansion. It is not one of the usual ones you see, and it's certainly not going to be one of the first ones you're going to see. When your professor starts talking about SP, SP2, SP3, you're probably going to spend at least a class period on that before he's going to spring this SP3D on you. And then even beyond that, they can spring they can spring on you this, which is even more complicated, which is an octahedral. I have to take my Tinker Toys apart, which is where you have 2 going up and down, and then we're going to center 4 of these different electrons around the center. So now if you can see it, keep in mind there's 1 going down, but we have 1, 2, 3, 4 around the center, and then 1 going up, 1 going down. You don't see a lot of these, but you will probably see at least 1 of the 2 of these. sp3, d2, that's 6 areas of electron density. Now, these are not more common. Both of these are due to a d-octet expansion. Now we're going to talk about so here's basically how you break the difference between electronic geometries and molecular geometries. Electronic geometries, they include all areas of electron density. But molecular geometries, they include only connections or only bonds from one atom to another. The key point that makes them different is that electron pairs are not counted. And that gives rise to some unusual molecules. We would say that this is CH4. It's carbon with 4 hydrogens around it. So it's sp3. Everybody's the same. And this would have an electronic geometry. When there's 4, it's tetrahedral. And its molecular geometry is the same. But if we had NH3, let's think about our NH3. If we have NH3, that would be nitrogen. We would say 1, 2, 3, 4, 5. And then you draw a hydrogen here, a hydrogen here, and a hydrogen here. Because when you draw your Lewis structures, you draw solo electron to solo electron. So this is what hydrogen looks like. Up top, there is no bond to another. There is no bond to another atom. So what happens if we were to try and draw it in our giving it dimensionality on a flat surface? The best attempt to draw this would be nitrogen with a set of electrons up here, and we show it kind of coming out like a strange little light bulb. We still have our hydrogen here. We have a dark hydrogen that's coming right out at us, which would be this one. So it's a deeper, darker line. And then we have a hydrogen that's going away from us into the paper. Still 4 areas of electron density, so it's still tetrahedral. But our molecular geometry is now going to be called, because the repulsion that you get from a flared out series of electrons is stronger than the repulsion that you get from just a single bond to this, the electrons will spread out and take up more space. Yes, exactly. So we call this is tetrahedral, this is tetrahedral, but when you get to this, your electronic geometry is tetrahedral, but your molecular geometry picks up a new name because this is flared out more, and we're now going to call this trigonal pyramidal. The same thing would happen if you had something like this. If we say had an sp3d, I'm going to move this. So let's say we had sp3d. That means 5 things. And let's imagine that we have 4 atoms bonded, 1, 2, 3, 4, and a lone pair of electrons. So when we have 4 electrons bonded like that, that's going to give us a different shape. That's going to give us a shape for our electronic geometry, since we include everything on this one. That's going to be trigonal, as in 3 areas of density around the center. Trigonal bipyramidal, as in there's a pyramid up top between 1, 2, 3 up top, and then 1, 2, 3 on bottom. So trigonal bipyramidal. But when you got to molecular geometry, because this is not another bond, if it was another bond to another atom, bipyramidal, bipyramidal. But because it's not, this is going to be a molecular geometry, and we're going to call this seesaw. If you think of the old seesaws, which I don't understand they don't have in parks anymore, it's seesaw. Look how it just teeter-totters back and forth. That's why it's called seesaw. Like so. If there was only one bond and you still had 5 areas of electron density, that's what's called T-shaped. So seesaw, sometimes they will abbreviate seesaw. They will abbreviate seesaw as, they will call it SP, well, they'll use A, B, 4 things, and then 1 unpaired. Versus if it's T-shaped, and the T-shape comes from, if you're looking straight down on it, here's our T, our crossbar, and then our standing bar. That's our T-shaped. T-shaped is sometimes abbreviated as A, B, 3, U, 2. Not the band, it's just saying 2 unshared, 2 unpaired sets of electrons. That's our unpaired series. This is electronic geometries and molecular geometries. You'll be seeing more of this. If you get to a point, if you have questions about it, it's certainly something that can be talked about in more detail. But there's one last handy piece that I want to give you about the periodic table, and that's patterns in the periodic table. Patterns in the periodic table. There are 4 patterns to know, and I make a study sheet, and I suggest you make a study sheet when you start doing this. We'll start with a cross, and we'll just make a giant box with a crossbar in it, and we have 4 patterns to know. That's electronegativity, We have electron affinity, ionization energy, and our last one is going to be, that's going to be our atomic radius. These are actually not too bad because we can draw a general pattern out here that says as you go up and to the right, your electronegativity increases. Electronegativity is the degree to which an atom wants another electron. So our electronegativity increases up and to the right. That's why fluorine and chlorine and oxygen are negative. That's why when you have things down here in this column, which would be francium, cesium, and barium, they are positive. They don't want to hold on to them as much. These guys really want to hold on to them. And if it sounds like electronegativity and electron affinity are related, they are, which is why the pattern here is the same. It increases. Now, ionization energy follows the same general pattern, which is that it increases up and to the right. It generally increases. I say generally increases because when we talked about our P's, we talked about P having 3 orbitals. Our most stable condition for a P would be for everyone to be completely filled. That's our most stable configuration for P. That's most stable. Our next most stable is half filled. Just one in each one. Anything that's not completely filled or half filled is less stable. These are the 2 best ones, so they have the highest stability, so they will have the best ionization energies generally. It's just a bit of... Right, so this is the one, this is the departure for our atomic radius. Our atomic radius increases opposite. It increases to the left and down. And this is why fluorine is very, very small up here. And so the electrons are very close to the nucleus. Let's remember that electrons are negatively charged, and the nucleus has protons in it, so it's positively charged, so they're very, very close together. So they really don't want to let go, which is why the electronegativity is so great and the electron affinity is so great up here. Versus, so if you were to draw a fluorine would look something like this. You'd have F with a very, very tight series of electrons around it. Versus if you were to draw francium down here on the far end, this would be francium down here. Francium is here, and then its electrons are much farther away. So these negatively charged electrons are much farther away than this positive nucleus, and they don't hold on as well. Last piece about what we're talking about atomic radius. This really is the last thing for today. I know it's gone a little bit long, but the last thing for atomic radius is ionic radius. So positive ions, now keep in mind, if it's a positive ion, it has lost electrons. We're never losing or gaining protons because that changes the element. Positive ions shrink. They shrink up and they get very small, very tight. So positive ions shrink based on where they started. Think of this as if you're a parent. If you're 2 parents and you have 1 kid, you can keep a real close eye on that kid. If you're a parent and you have 2 kids, you have to keep an eye on them about equally. But if you have more electrons, if we have a negative ion, which these are generally going to be our non-metals, our positive ions, I'll just write in here, these are generally metals. Not always, but generally metals. Our negative ions are almost always going to be non-metals. In fact, with the exception of some very specific processes in the body, if you can find a metal that's going to be a negative metal outside of the human body, you let me know, we'll patent it, and we can both go on a vacation. I'm going to go live on a ski slope, and you go do whatever you want. You probably won't have to study anymore. Because if you find a metal that's negatively charged, you're going to find something that no one else has really found. And again, that's with the exception of a few very specific biological processes. We're looking for metals to be negative outside of the body. It just doesn't happen. Negative ions, they expand. And think of this as if you have, the more kids you have, the more freedom you have to give them. You can't keep as close an eye on them. The electrons now outnumber the protons, and so instead of having something like, if this was our normal one for this, if it became positive, it'd become even tighter. If this is our normal one here, if it's negative, it's going to have a much larger radius now, because the protons cannot hold on as tightly to the electrons. So we've covered a lot of ground today. I'll try and do a very quick review. We reviewed our periodic table with our alkali metals, alkali earth, halogens, noble gases. We talked about the step point between non-metals on this side, metals on this side, our metalloids along here. We talked about electron configurations. Our S is this column, or these two columns over here. Our P is this set of 6 over here. Our D is in through here. Our F is through here. We talked about drawing our electrons. Our S can have 2, our P can have 6, our D can hold 10, and each orbital has 2 electrons. So this would be 1 orbital for P, 3 orbitals for, 1 orbital for S, 3 orbitals for P, 5 orbitals for D, 7 orbitals for S. We talked about iron. We showed it expanding into the D. We talked about quantum numbers. Our N is our energy level. Our L is our angular momentum, and it's always N minus 1. Our M sub L should always be values between negative L and positive L. And our M sub F is just our spin. We always say spin up, spin down, positive, then negative. We talked briefly about, this will be later in the semester when you start talking about light and frequency. We talked about how if you excite an electron, this is tied into quantum. If you excite an electron, it expands out, and when it falls back down, it emits a photon of light. We then talked about N sub L. We talked about VSPER theories, areas of electron density. This is talking about valence shell pair of electron repulsion. They want to be maximum distance apart. When it's 180, you can draw it on paper. When there's only 3, it's 120, you can draw it on paper. An area of electron density is a pair of electrons, or a single bond, or a double bond, or a triple bond. We do CO, which has 2. We do acetylene, which would also have 2, so this would also be SP. We looked at BH3, which that is 3, so now that's 120. And then we talked about trying to draw things with more than 3 in 3 dimensions. The dark line means it's coming out at you. The dashed line means it's going away. And then the distinction between electronic geometry and molecular geometry. Electronic geometry includes everything. Molecular geometry only includes the bonds from one atom to another. Electron pairs are not counted. So when you have pairs of electrons that are in there, your molecular geometry will change from your electronic geometry name. And we finished with patterns in the periodic table. They are all related. Even the electronegativity, which is greatest up here, and electron affinity, which is greatest up here. There's a reason why, because your radius is much smaller. It's more tightly bonded. And these down here are much farther away, so they are loosely held onto. That was a lot about the periodic table. This will be available online. We're going to have the link for you and the location to where it is shortly. Next week, we're going to start talking about nomenclature. Nomenclature is one of the things that gives the students the greatest problem, but I think you're going to find it's not so bad. I'm going to divide it into 2 parts, and then each part has 2 options. So there's really 4 options that you need to learn, and then we're also going to talk about our most common polyatomic ions. Myself and a couple other colleagues went through one of the chemistry books about a semester or 2 ago, and one of the things we noticed, if you know about 10 polyatomic ions, that's going to be about 90% of the questions you have. My name is Pat. Thank you guys for being here. I'll hang out for a little bit if you have some more questions, but that's it for the material for today. Thank you.